Hello, this video is a lecture for Chemical Engineering Thermodynamics I, and we are at lecture 2B. In the past lectures, we talk about the first law of thermodynamics, and we apply the first law of thermodynamics to closed system and also to open system. And during the derivation, we come up with two variables, heat capacity and enthalpy. For this lecture 2B, we will move on to a new lecture within the textbook, a textbook written by Professor Smith. And the content would start with the phase rule. Phase rule is basically an equation written like this, where F is called degree of freedom, pi is the number of phases within the system, and N here is the number of chemical species within the system. You can use this equation for closed system, isolated system, or even open system. Okay? The application of this equation can be shown here. First, if I have a bottle containing water, and on top of this water I have air, so there's air as well as some water vapor evaporating into the air. If we use the equation, the number of phases inside this closed system is 2. We have liquid phase and we have vapor phase, right? But for the number of chemical species, in this case we have 2. We can think of 2 species, water and air. But some of you might wonder, should we use the word air instead of oxygen and nitrogen? Okay, you can you can use oxygen and nitrogen instead of air. In that case, the number of species would be 3. Okay, but as long as air and nitrogen are combined with fixed composition 21/79 mole ratio, and as long as you can find the properties of such mixture, just like the air, we can find or we can calculate density of air as a number at some certain state. In that case, we can still combine oxygen and nitrogen and call them to be another pure component called air, right? So if I treat air as one single chemical species, in this bottle there are 2 species, water and air. So therefore the degree of freedom would be 2. Alright? Another example is this boiling water. You should see that my kettle here has opening. If the heat is applied continuously, my water here under atmospheric pressure, because there's an opening here, so pressure inside here and pressure outside is supposed to be equal at 1 atmospheric pressure. So for a while, air inside this area or this volume would be purged out by the steam generated. So if I draw the system boundaries around this kettle, okay, the system would become open system. In this system, I will have only 1 species, which is water. Inside the volume here, there's pure steam, which is pure water, no air, because we assume that air was purged out already. Okay, in this case there are 2 phases, liquid and vapor, but only 1 single species, which is water. So if you apply this situation to the degree of freedom calculation, you get F equal to 2 subtracted by 2 plus 1 equal to 1. That's mean degree of freedom is 1. The question would be, why do we have to calculate such a number? What is the meaning of degree of freedom? The meaning is very simple. Degree of freedom tells you the number of intensive properties. Okay, I would like to emphasize on the intensive properties. The number of intensive properties needed to fix the state. What does it mean, fixing the state? Okay, it basically means that if you know the variables at the same number as the degree of freedom, then you can calculate other variables at that state. For instance, if you look at system B, the degree of freedom here is 1. Okay, so if you state that pressure is 1 atm, other variables like temperature, volume, even internal energy or enthalpy can be calculated or must be calculated or must be comply with this 1 atm. Okay, in reality, if you see the boiling water like this, and if you know that the pressure is 1 atm, you can tell right away the temperature is 100 degrees Celsius, right? So this 100 degrees Celsius complies with this pressure because the degree of freedom is only 1. So as long as I state one variable, the other variables can be calculated from this one variable right away. Okay, we can never state the number of variables higher than the degree of freedom. So if degree of freedom is 1, we cannot say that I like to get the pressure to be 1 atm and temperature to be 120 degrees Celsius at the same time. For this picture, you cannot do that. In that case, it will be over specification. Okay, so in this case, if the degree of freedom is 1, you can state only one variable. If you state pressure, the temperature can be calculated to comply with that pressure. If you state temperature, that pressure would comply with temperature. Okay, you can also obtain that the specific volume of water, in this case for liquid water, would be 1.044 cubic centimeter per gram from this specification of the pressure. Okay, so plainly, the number of degree of freedom would tell you how many variables you need to obtain before you can calculate other variables. Mathematically, you can say that one single variable or one single properties can be a function of the number of variables. That number would equal to degree of freedom. Just another example, if you look at system A. In this case, if I specify the pressure inside the bottle to be 1 atm, what should be the temperature? Okay, if you look at the picture, you cannot say the temperature for certain. You can say that this one is 25 degrees Celsius or this one is 40 degrees Celsius. It will look the same, because specifying only pressure is not enough to fix the state of this picture. Okay, in order to fix the state of this picture, you need to specify both pressure and temperature, because the degree of freedom is 2. So if I say that the temperature is 25 degrees Celsius, for the system where pressure is 1 atm and temperature is 25 degrees Celsius, now the state is fixed. Then you can calculate other variables. For instance, specific volume of water at this state would be about 1.003 cubic centimeter per gram, or the density of water would be about 1 gram per cubic centimeter. Okay, now for system with one single component and one phase, okay, this is the most system that we will describe in thermodynamics 1. In that case, the degree of freedom is 2. That means we will need 2 properties in order to fix the state. Or we can say that any kind of state properties must be a function of two other variables or two other properties. I'll give you an example. Oh, by the way, these two properties, in general, we would prefer to have measurable properties, because as long as we can measure them, we can calculate other properties. For instance, if you want to calculate enthalpy, you can say that enthalpy would be a function of two variables. In this case, if you pick two variables to be internal energy and then temperature, the internal energy by itself, it is impossible to measure, right? So such definition would not give you any advantage in calculation. On the other hand, if I say that I would like to define enthalpy as a function of two variables like temperature and pressure, both of them are measurable, then after measuring or after obtaining these two variables, we can calculate enthalpy. In thermodynamics, three variables or three parameters, three properties are measurable. Those three are temperature, which can be measured by thermometer. Pressure can be measured by pressure gauge. And then volume. You can measure dimension using maybe measuring tape and then calculate volume from the dimension. Or you can measure the volume directly using fluid or using measuring cup. Okay? Just an example, if I would like to get the number for internal energy, in this system where degree of freedom is 2, I need to specify two properties. Okay? That means mathematically I can say that I can write internal energy as a function of two variables. And if you are more familiar or if you have experience in thermodynamics, you see that whenever we would like to calculate internal energy, it would be much easier to define internal energy as function of temperature and volume. Okay, I will show you why in a minute. From calculus, if you modify the chain rule, you say that whenever you have U as a function of temperature and volume, total differentiation of U can be written as a combination of two terms. The first term would be partial differentiation of U with respect to temperature when the volume is constant and multiplied by dt, and the second term would be partial differentiation of U with respect to volume when temperature is constant multiplied by dV. This equation is basically defined from calculus. It has nothing to do with thermodynamics at all. Okay? The first term on the right hand side, this term, if you recall from lecture 2a, during lecture 2a, I plot between U as a vertical axis and then T as a horizontal axis, and then we say that the slope of the function at any temperature is defined as a du by dt, and that is called CV, or heat capacity at constant volume, right? This term, on the other hand, you have never seen before. This one we will derive in lecture 5a after we will learn about some more relationship, some more thermodynamics relationship. That this term can be further derived into this term, into this equation. Okay, but the detail for derivation I would like to just skip for the moment. I would like to show you the application before we going through the derivation. Okay, I believe that when you see application, it would be easier or it would be more convinced to do derivation. So just trust me on this, that the blue term can be converted into this term, right? The good thing about this term is that, as you can see, all variables are measurable. Okay, we can convert something that we can never measure into whatever we can measure using some relationship. Okay, but in order to take derivative here, you have to know the function of pressure before you can take derivative with respect to temperature, right? So relationship between pressure and temperature must be known. That relationship will be described in lecture 3a, okay? The relationship between pressure, volume, and temperature is called equation of state, and we will learn that in lecture 3a. One well-known equation of state would be ideal gas law, right? The relationship PV equal to RT is basically one single equation that we already learned, okay? After you know the pressure as a function of temperature, you can take derivative here, obtain this value, and then plug in this part of the equation. That means everything on the right hand side of this equation will be known, and then after integration you get delta U that can be further used in first law, okay? For the same system, this is still the same system, okay? You can also calculate enthalpy. But again, whenever you want to calculate enthalpy, it would be easier to define enthalpy as a function of temperature and pressure. Still, we need two variables because the degree freedom is 2. But these two variables will be easier to use temperature and pressure, okay? With respect to calculus, we can say that as long as enthalpy is a function of temperature and pressure, we can expand total differentiation of enthalpy to be these two terms, okay? The first term is differentiation, partial differentiation with respect to temperature when pressure is constant, and then differentiate it again with respect to pressure at constant temperature. Doing something like this, the reason I choose temperature and pressure is that the first term was already defined. This term was defined in lecture 2a to be Cp, or heat capacity at constant pressure. The second term highlighted in blue will be further derived using lecture 5a to get this relationship. Once again, this relationship all contain the measurable variables, okay? And if you know the function of volume as a function of temperature, then you can take derivative here and get the number. So relationship between PVT would be described in lecture 3a. Alright, so if you take derivative, calculate this term, plug into this blue term, whatever inside on the right hand side will be known and ready to be integrated to obtain delta H. Once you get delta H, you can plug into an equation for first law, right? And then you can calculate heat and work afterward. Alright, I'd like to emphasize that these two equations are applied on the same system. That means you have one certain system, you can calculate internal energy change using the top equation, and then you can calculate enthalpy change using the second equation, okay? And there are special circumstances that we can simplify the equation corresponding to some certain system. The first special circumstance would be the system with constant volume, okay? And this constant volume process can be either closed system or open system. This is constant volume process in general. If the volume is constant, the derivative dV would be 0, because dV physically it means change in volume. If dV is 0, whatever mass we have on the right hand side here would disappear, and we will get du equal to cv dt, which complies with what we learned from lecture 2a. Okay, we learned in lecture 2a that for closed system, if the volume is constant, then du would equal to cv dt. But this equation tells you a little bit further that it is not limited to closed system. Okay, as long as the volume is constant, then you can apply this equation right away. But for the calculation of enthalpy change, dH would start from this equation, but we can not reduce this term further because we have no clue about pressure change within the system. We only know that the system has no volume change, right? So if you want to calculate delta H for constant volume process, you have to follow this equation. Further specific, a little bit more specific for this system. If the system is closed system and constant volume, okay? So if the system is closed, that means the delta U would equal to Q, under the assumption that for closed system, according to the first law for the closed system, delta U equal to Q plus W, right? If we consider, or if our system has no non-expansion work and no non-mechanical work, just a reminder, the work can be divided into mechanical and non-mechanical. For mechanical work, it is divided into expansion and non-expansion, right? So if your system has nothing else, no work at all, no electricity and no stirring, so that means the only work that we are concerning right now would be expansion work. And for the closed system with constant volume, expansion work becomes zero. In that case, according to the first law, delta U would equal to Q, or du equal to del Q, right? So the blue part of the equation here was defined based on first law under closed system constant volume. The black letters here is what we got from here, okay? So if the system is closed system, then we can obtain that the amount of heat transfer would equal to integral of Cv dt. Alright, now I have another question. Can we use this instead? From the definition of enthalpy, H equal to U plus PV, if we take derivative, dH would equal to du plus d of the PV, okay? But in this case, volume is constant, so I can take the volume here out of the differentiation, and du would equal to Cv dt from this relationship, right? So I can replace du with Cv dt, and the second term would be vdp. Okay, can I use this equation instead of this messy equation? The answer is yes, you can, as long as you consider the same system here, the constant volume process. You can use this equation or you can use this equation. Both of them should give you the same answer. Alright, the question would be, which equation you have more information? For instance, if you have heat capacity, information about heat capacity at constant pressure, if you know Cp, you have no choice but using this equation. But if you know Cv, then it would be easier to use this equation, right? For another circumstance, if the process is constant pressure process, the calculation of delta U or du would be picked from this equation without further modification because we have no clue about the change in volume. Okay, we only know that this pressure is constant. But for the calculation of enthalpy, the dP here would be 0 because there's no change in pressure. The equation can be reduced into dH equal to Cp dt, which would be the same as what we described in lecture 2a for closed system with constant pressure. Okay? So you have to realize that these two equations are applied to the system with constant volume. These two equations apply for the system with constant pressure. So it depends on what kind of system you have in your hand. Okay? If your system is neither constant volume or constant pressure, then you have to step back to use these two equations. Understand? Another special circumstance is that when inside your system, or if your system is ideal gas, then in that case, if you look into this red term, okay, the ideal gas law states that PV equal to RT. So if I replace P by RT over V, okay, and take derivative here, please note that the derivative is taken at constant volume. So V here would be treated as constant, R is constant, both of them can be taken out of the differentiation, leaving dt by dt, which is 1. So you get R over V as a result for this red term. If you plug this R over V to here, then you get RT over V, which is also pressure. You get pressure back according to the ideal gas law. And pressure subtracted pressure, this term becomes 0. Okay? So the first equation here, if you apply for ideal gas, you end up with du equal to Cv dt. Even though it looks as if it would become the same as the system with constant volume, the situation are totally different. Okay? They just produce the same equation. You have to realize that the situation are different. If I apply the same thing here for the green term for the calculation of enthalpy, then V would equal to RT over P. You take derivative under constant pressure assumption here. It states here that the pressure is constant. Taking derivative, you get R over P multiplied by T and use ideal gas law again. You see that you get volume, which would be cancelled with this term. The whole term highlighted in blue would be 0 again. So for ideal gas, the enthalpy would equal to Cp dt, just like what we obtained from the system with constant pressure. But again, if your system is ideal gas, these two equations are correct. Okay, you can use both du equal to Cv dt and dH equal to Cp dt at the same time. If your system is not ideal gas, let's say your system is constant pressure without being ideal gas, the du will not be Cv dt. It would follow this equation. Okay, this is only special circumstance when the system is ideal gas. And then, if you take the definition of enthalpy, H equal to U plus PV, and you take derivative, you end up with this equation. Okay? Note that this is the differentiation of a product, PV. And according to ideal gas law, PV equal to RT, and R is constant, you can take it out from the derivative. You end up with this term, dH, according to this equation, is Cp dt. du from this equation is Cv dt, right? And all dt's can be dropped so that you get the relationship between Cp and Cv if your system is ideal gas. You may already learn this relationship from physics, but we can use the derivation in similar manner if your gas is no longer ideal. By using the same concept, you can calculate or you can make approximation of the relationship between Cp and Cv for any substance. But of course, if it is not ideal, the equation will be much more complex than this. Now, once again, these two equations are applied for the calculation of du and dH respectively. In this case, if I apply to closed system, okay, starting from initial state, after receiving heat or work or releasing heat or work, you end up with final state, starting from U1H1 and end up with U2H2. Similarly, if the system is open system, okay, the input into open system may have the properties U1H1 and output of the open system may have properties of U2H2. We learned that these equations are applicable for both systems. They are not limited to any closed or any particular system. Okay, you can use them for both closed and open system. For open system, U2 would be the properties of the output stream after the stream has passed the whole system. So it seems to be the final state after the process or after the change, in similar manner as what we described for closed system. So this state for closed system is after the process has done. Okay, this state for open system is after the stream has passed the whole process. So in the sense, they are the same. Now, if I draw a diagram between pressure and temperature, okay, if the starting point at state 1 has the temperature of T1 and pressure of P1, and at the end, at the outlet, the temperature would become temperature T2 and pressure P2, okay, and the red line here is the path that the system took. Okay, at the initial point, the enthalpy is H1, and the end point enthalpy is H2. Again, this diagram is not limited to open system. It is applicable for both closed and open system. Okay, I just show you the open system for convenience. Now, the change in enthalpy for this path is called delta H12, just from 1 to 2, from point 1 to point 2. Okay, in short, I call this one 1, 2. By definition, delta H12 is the state of enthalpy after the process or at final state, subtracted by enthalpy at initial state. So H2 subtracted by H1. But sometimes it would be easier. Sometimes we may have more information on some other path. Okay, the red path here is called direct path, but sometimes it will be more difficult to calculate it from direct path, or sometimes information for the direct path is limited. So it might be easier to go or to choose another path. The indirect path is shown here as the blue line. Okay, let's say if I start from state 1, I can go to state 3 first. The state 3 has temperature T3 and pressure P3, and then move on from state 3 to state 2. Okay, the blue line here represents indirect path, and you have a freedom to choose your own indirect path at your convenience. Okay? If the first step here is called H13 from 1 to 3, and then the second one is called H32, we can get relationship that delta H12 equal to delta H13 plus delta H32. Mathematically, you can say that delta H12 is H2 subtracted by H1. Delta H13 is H3 subtracted by H1. And then delta H32 is H2 subtracted by H3. So H3 here from here would cancel out. Okay, and then you get the left hand side and right hand side to be equal. In other words, you may also say that enthalpy is a state property. So therefore, it doesn't matter whether you calculate enthalpy from the direct path, the red line, or the blue path. It doesn't matter. You end up with the same enthalpy change. Okay, so delta H12, according to this picture, is basically the calculation from direct path, and the terms on the right hand side are obtained from indirect path. If I rotate the angle of the graph, if I change the graph from 2 dimension to 3 dimension, showing this enthalpy as well, okay, it might be a little bit clearer. The first state, the first point, should have temperature T1 and pressure P1 with enthalpy H1, where the second state here has temperature T2 and pressure P2, enthalpy might be H2. Okay, the path will be maybe in any form, any function. In this case, I just draw the red line here. H1 and H2 can be read from the vertical axis, from this enthalpy axis. Okay, so H12 is basically the gap or the distance between these 2 points. Okay, now the red line is direct path. If I take indirect path from 1 to 3, from point 1 to point 3 first, okay, and from 2-dimensional diagram earlier, the 1-3 path is basically constant temperature. So point 3 here still is at a temperature T1, and then another pressure, a pressure P2. Okay, the enthalpy of this point can be read as H3. Okay, so I can go from point 1 to point 3 indirectly. I'm sorry, instead of going from point 1 to point 2 directly, I can go from point 1 to point 3 and return to point 2 as an indirect path, the blue path, like that. Okay, so in this case, H13 is a height from point 1 to point 3, representing by these green arrows. Okay, H32 is going from point 3 to point 2, representing by purple arrows. So if you take the green one subtracted by or added to the purple one by considering direction as well, you add them like a vector, then what you have left would be this distance, which is delta H12. Okay, so the point of this diagram is to show you that sometimes it is easier to calculate by indirect path. There are 2 scenarios that it would indirect path would be preferred. The first scenario is that whenever the information needed for the calculation indirect path in the red path here might not be enough or might not be available, okay, we will choose another path that we have information. The second scenario is that sometimes the direct path requires difficult mathematical integration, or the math representing the red line is somehow complex, would be difficult to integrate or to differentiate. It would be easier to use another path that we define to avoid complicated mathematical model. Okay? So the point of this lecture, I just introduced first would be concept of degree of freedom. Basically, it tells you the number of variables you need to define before you can calculate other variables. Then I show you examples to calculate internal energy and enthalpy. Okay? And lastly, for this lecture is this diagram, is to show you the idea of using indirect paths to calculate the change in state properties, because sometimes it is easier to use indirect paths. Okay? So the next lecture I would describe more into the calculation of delta H. Thank you for watching.